Hello, let's wrap up energy and work with our last video, conservation of mechanical energy. Now, the potential and kinetic energy can be related of an object can be related to each other in simple systems, and we're only dealing with very simple systems in physical science, and you'll get the idea when we do a couple of examples. Within these simple systems, energy is conserved, so we're assuming that nothing's being lost to heat and friction and things like that. So let's look at this simple system. You're throwing a baseball up and catching it at the same height. Down here, as it leaves your hand and just before it hits your hand, it's got the maximum kinetic energy and the minimum potential energy. Maximum kinetic energy because it has the maximum velocity. Minimum potential energy because it's at the lowest height. Now as it goes up, it of course, if we remember from projectile motion and our equations of motion, because hey, physics is all related to each other, it's going to slow down due to gravity, and so just at this instant it would momentarily stop, so its velocity would be zero. So it would have the minimum kinetic energy. Now where's all the energy gone? Well, it's now gone into potential energy, and the potential energy is at a maximum up here, and then as it falls it gains in velocity, so its kinetic energy increases again and its potential energy decreases as it's losing height. So when objects are lifted they gain potential energy, when they fall they gain kinetic energy. So this is another example. In this case we're just taking a 2 kilogram box, lifting it up onto a bench or a tabletop or something which is 5 meters high. So the work done, because we're applying a constant force, moving an object up 5 meters, is now the weight force, 2 kilograms times by gravity, I think they're using 10, we would use 9.8, is approximately 100 joules, so that's the work done. So the potential energy up here must be equal to the work done, because this is a simple system. If we're doing work, energy's got to go somewhere, and it's going into this box. So when the box up here has 100 joules of energy that the box down here doesn't have, because you've done work, basically. That's what it's saying. Another example, let's consider a ball dropped from a high cliff. So here's a high cliff, seems to be a monster ball, but it's going from here to here, and we've done these sorts of questions in our motion questions, so we should be understanding what sort of changes in velocity are undergoing. So if the ball had a mass of 1 kilogram and the height was 100 meters high, we can calculate the kinetic energy and the potential energy at any stage in going from here to here, because up here the kinetic energy is 0 and it's at maximum potential energy. Down here, just before it hits the ground, it's got a maximum kinetic energy and its potential energy is 0. Now we can put that into a table, but before we do that we must recognize that at any point we can look at any point here and work out the kinetic energy, because we could work out the velocity, couldn't we? And because we could also work out the height at any point here, we could work out the potential energy. And when we add it up at any point, the sum of the two is equal to the potential energy at the start. What does that mean? Well, here we are at 100 meters. The potential energy is 1000 joules, just to use nice round numbers. The kinetic energy is 0, so the total potential energy and kinetic energy is 1000, and its velocity is 0. Now as it falls, what's happening? It's losing potential energy. I hope you can hear my dog there. She's eating a smacker, making a lot of noise. If you listen carefully you'll hear her. But as it's falling, its velocity is increasing as it's getting faster and faster due to gravity, so its kinetic energy will be increasing, because that's half mv squared. But as it's falling, its potential energy is decreasing. But notice here the total of the potential energy and the kinetic energy, it's always the same, so energy is being conserved. Again, we're talking about a simple system, so we're ignoring air resistance and friction and everything else. and sound. But in our simple system, energy is conserved. Hope you understood that. So another example that we use are roller coasters. There's a pretty fun roller coaster. These guys are hanging with their legs out, going around. Fantastic. There's a very big roller coaster. And there's one that goes all over the place. Unfortunately, we don't have any good roller coasters in Tasmania. Don't think we have any. But if you get a chance, go on a roller coaster. Good fun. So let's look at a very simple one for us. Here's point A, B, C, D and E. Here's our roller coaster. So this is a graph that describes the energy as it goes along the track. And the solid line here is the gravitational potential energy, and the dashed line is the kinetic energy, and then the one that measures the envelope is actually the total energy when you add the two together. And so here, up here, it's at a maximum potential energy and minimum kinetic energy. Then it goes down. Here it's got a velocity, but it's still got some height, so it has a bit of potential energy and a bit of kinetic energy. Here it must be moving the fastest because all the potential energies become kinetic energy, and so it's moving the fastest just there. And then it does a loop-the-loop, and so at point D it's now got some potential energy and it's almost stopped. Clearly it couldn't have zero velocity because it would just get stuck there. Alright, now notice that A is higher than D because what we're saying is that energy is being lost. Now this is an unusual question. Usually we just ignore friction, but it's good to know what's actually happening in the real world. And this energy lost would be the sound, friction from the wheels, air resistance, all those sorts of things. And that's why you could never have a loop, the loop, that was higher than A. And it's always got to be low, and it's always got to be having a velocity there. So they should have shown it D. I would have put D somewhere there, and even not have shown it stopping. And then E gets to there. So a little bit more complicated, but hopefully we understood what was happening there. Now this is a nice little animation that shows exactly the same. Got to watch it a couple of times. And this is the, notice that when the potential energy goes up, the kinetic energy stays down, and the kinetic energy goes up, potential energy goes down, and it's always a balance, and if we added any of those up at any time, they'd equal the same amount. Well, that's the idea anyway. Alright, just makes it through the loop. So now you should be able to do, there should be a simulation on the OneNote with the roller coaster and maybe a quiz if it works. I haven't tried it in OneNote, but hopefully it will work. There is a video from ClickView, and that's going to be just watch the first 12 minutes, and I'll have a link to that. You'll have in your booklet you've got conservation of energy questions to do. There's another video that's a ClickView video that will be in your OneNote, plus there'll be some revision questions for you to do. So once you start doing revision questions, what does that mean? You must be at the end. And that's it. So see you later.